Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, welcome to the talk this morning. We are pleased to have Alin Dobra here, who has done some very, very interesting work, not only what he's going to talk about today, but the prior work on approximate query processing that he did with Chris Jermaine. It's an utterly interesting piece of work and has as such been recognized. I became aware of this actually at this last SIGMOD, and I thought this was one of the absolutely most interesting papers in the whole conference, so we decided to invite Alin, and he's going to tell us more about it, and we'll dig into all the details. So welcome.
Thanks, Paul, and I'm glad to be here. Now, before I even go into the talk, I want to make sure that you understand that I really encourage people to ask me questions. I am fine with if you try to break my rhythm or whatever. I'm going to reorganize parts of the talk anyway. So I think it's more important to nail down things that are on your mind on the spot. I might defer some of the questions if I have some slides later, or if you're overly eager, I might jump ahead. But okay. Now, something that I will try to do is to give at least a mini demo. I was trying to give a bigger demo, but I just realized one of the constants is wrong in my program. It will be enough to give you some kind of a glimpse of how this works, to have some idea that it's not only kind of theoretical work, mostly because I'm a theoretician, so people like me have the tendency to propose things and not necessarily do them. So this is joint work with Chris Jermaine, who now moved at Rice, and a number of students and postdocs. One of them is here, Fei Xu, right there. Right? And the idea is going to be centered on a new paradigm of designing database systems. This is really a ground-up design, something that at least it's meant to be novel. Okay. All right. So let me give you some background of the kind of research I've done up to this point to put things in perspective, and I'll try to make some points for the talk of why this might or might not matter. So I really spent about 10 years on approximate query processing, work on sketching, histogram sampling, and I want to mention the work on DBO with Chris Jermaine, right? That the idea in DBO was to combine query execution and online approximation, right? So that you get an idea of what the answer is going to be as you go along. Idea being, if I'm running on terabytes or higher, it's going to take a while. So at least I'm not going to be so bored and I see the confidence interval is dropping. But maybe it's not the right question to ask and you kill it. It's a very interesting problem, right? So we were able to show that under wild conditions, basically you can give shrinking confidence intervals for aggregate kind of queries. We dealt with joins and complex aggregates. Now, from the point of view of the system that we implemented that was running DBO, we did everything by the book, right? It was a pool-based architecture. We used pipes and operator trees to move data along. We got PostGRES-like performance for the exact answer by the time you actually finished. And by seeing only about 10% of the data, you already had good approximation for the sampling process. So you could argue that it was 10 times faster if you only asked for good approximation for the whole thing, right? But I mean, in the end, the system is really not good enough. And the reason is, by using 8 cores, we cannot keep up even with one hard drive. And this is 2007 kind of hard drives doing only something like 40 megabytes per second. We had 4 hard drives in the system. So it looked like, even though we tried to be very careful with respect to the implementation, there is something there with respect to the speed at which you can actually process. The mantra in databases is hard drive is slow, the CPU is fast, and we've been hearing this for many years. What I'll try to convince you in this talk is this is far from the truth. We can now do linear scans that are so fast, it's very, very hard to keep up with them. Okay. So how did I get to actually design a system like DataPath? Well, it just happens that we got an NSF grant, and we promised in the grant that we are going to scale DBO to 1 to 10 terabytes. Okay. Now, at the time, DBO was running on 20 gigabyte instances, about 10 minutes to do some queries on that. So we got support for 4 students, but more importantly, we got $60,000 in hardware. Now, why am I mentioning this? Because I want to talk a little bit about also, later in the talk, what kind of things we bought with the $60,000, right? There are really 2 schools of thought. One is to buy basically clusters. And we could have bought, stretching the money a little bit, about 20 nodes, maybe closer to 50 nodes. And one possible idea to scale DBO from the 20 gigs to something larger was maybe to use the MPP approach, right? Set up multiple machines, do some kind of talking between them. And really, if you do that, you have some hopes to scale by a factor of 20. Well, under ideal scenarios, right? So there was some hope that we can deal with 400 gigabyte databases within 10 minutes, okay? But that's a far cry from scaling to 1 to 10 terabytes. So it's clear from the beginning, if that's your goal, that's what we promised, then you have to do something a little bit different. Okay. So in the end, to scale, you would need about 20 times the hardware. You can always say my software scales, so if you would throw more money at it, you would get your terabytes. That's not exactly a satisfying solution to us, right? So now, especially for me being a theoretician, I like to ask fundamental questions, which is, could you redesign the system so it can actually tackle for under $100,000 terabytes size? Now, let me give you an idea of why that might be possible, at least if you ignore what software is out there and you look only at hardware capabilities, right? So the storage actually is very cheap nowadays. It's one terabyte hard drive is $80 to $100, okay? Now, compare this with our processing capabilities. You really need $1 million hardware to have any hope to do terabyte scale processing with existing hardware. But even more importantly from the point of view of the hard drives is the disks have actually very high throughput. Okay? We are not anymore in an age where you can do a couple of megabytes per second. A $100 hard drive can do 150 megabytes per second. We just bought hard drives like this. Now, let me give you an idea of what that's the case. The SSD manufacturers, the solid disk manufacturers, put a lot of pressure on the mechanical disk manufacturers. In order for those guys to survive, they basically just made everything a lot more streamlined, and now mechanical disk can do 150 megabytes per second. Of course, SSD can do even more. And I just acquired 2 of these hard drives, very interesting toys, $4,000 each, which basically they are PCI cards. They have 16 independent SSD memory chips on them and an onboard RAID controller. Now, you might think that's a high price, but I'm going to argue later that if you are willing to pay for throughput, not for capacity, this is actually the best you can actually buy right now. Okay? In particular, those hard drives, at least theoretically, the manufacturer says I can do each of them 1.4 gigabytes per second if you do scans, linear scans. I'll get back to that in a second. Now, if you're looking at processors, right? Processors, $100 can buy you 6 gigaflops per core, which is about 24 gigaflops for $100. So if you look at query 1 in TPCH, I'm going to have to say a lot of things about query 1 in TPCH. The reason is it's one of the most dreadful queries. Whoever ever did TPCH benchmarking, right, they could speed up everything except query 1. Okay? So I'm going to talk a lot about why is that the case and what's going on in there. I have the query 1 on the next slide, but basically what's happening is query 1, in principle, it's a very simple query. It requires a scan of line item, but it has 8 aggregates, relatively simple. Right? And you're forced to read 95 to 97% of the line item. There is no database trick that's going to help you there. No indexing, nothing. Okay? And literally, you need to perform about 30 flops per tuple. It's actually closer to 17, but if you're sloppy, about 30. And if you multiply that with the number of tuples at 1 terabyte, which is 6 billion, you get about 180 gigaflops, which is about 8 seconds worth of a $100 processor CPU. If you look at purely from the flops point of view, ignoring everything else. Right? So that basically suggests that query 1 should be definitely I/O bound, because I need only 8 seconds to do the processing and about 60 seconds to read it from the disk, if I read only columns, if I'm smart. Right? So I should be able to do 8 independent query 1s in parallel and still keep up with the processing with my these fast hard drives. Okay? Well, it turns out that's not the case. If you look at the published TPCH benchmarks, the best non-cluster performer is an HP Superdome. It's a $1.7 million and does 142 seconds for query 1. And with no possibility to do multiple query 1s in parallel. I mean, it scales linearly with the number of queries. And that machine has 64 cores, half a terabyte of memory, 576 disks. You cannot argue that this disks don't have more throughput capacity than my two the Z drives, right? So everything theoretically about this machine suggests that it should be much, much better. Running time does not reflect that, right? So this talk is going to be a lot about what's going on in there and what can you do about it and how we came to have much better performance on that query 1, okay? Now this is the dreadful TPCH query 1, okay? It's basically a scan on line item. Filtering condition is very simple. You're basically just saying everything up to almost the end of the relation, right? There is a group by. I'm going to ignore it because it's a group by on 2 attributes. All of them have 2 possible values. There are only 4 groups. It doesn't really matter how you do the grouping in there. But this is the part that actually creates significant problems for all the databases on the market. Right? It's not even that hard. I mean, you're talking about relatively simple expressions, but quite a lot of them. So this is why you have to do those 17 to 30 flops per tuple, because you have to evaluate these expressions and you have to maintain the running sum, running averages. Okay. Now, why I insist on this query 1? You see, if we really hope to do some massive scale, interesting statistical analysis on data, and that's obviously the goal for all of this analytical query processing, this query is very simple compared to what we would like to do on the data, right? Almost any statistical model is going to be a lot more complicated. Think about some linear regression in there and so on. I mean, you're going to have to do a lot more flops per tuple, okay? If you're not doing fantastically well on this kind of a query, there is really no hope to go and do very well on things that statisticians are going to come up with. Okay. And if you look at, for example, how statisticians use databases now, through SAS, they pretty much use the database to get in the order of 1 million tuples, and they do the statistical analysis on 1 million tuples. Nobody does billion tuple statistical analysis. Okay. So my personal interest is in setting up things so I could do that. So let me show you why there is hope. Now, I'm going to talk about another query, which is query 6. In query 6, it looks very similar to query 1, except that the aggregate is much simpler. Right? I have a simple expression, but the filtering condition is complicated now. So I have about 5 independent conditions that I have to evaluate. Now, this query is very interesting because it's a query on which all the great database stuff like indexing should help. But I'll argue, and Mike Stonebreaker was arguing for a long time, indexing doesn't really help. So let me explain why it should help, and later I'm going to explain why it doesn't help. If you look at the typical parameters for query 6, only 1 in 50,000 tuples actually passes the predicate. Okay, so the selectivity is tiny, 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 tiny. This is why this aggregate, by the way, doesn't matter. I could put here an enormous aggregate. You aggregate only over 1 in 50,000 tuples, right? But if you use very, very clever indexing, it's still going to be hard to beat potentially linear scan solution, even though the selectivity is so high. Which basically means indexing might not be that useful for this kind of large databases. It's not only my observation, it's other people who are saying this. Okay, so I'm going to do a number of case studies just to give you a more idea of what might be going on in there and what can you actually expect. Of course, I'm going to talk about DataPath, our system, as well, and put things in perspective. Okay, so what I want to talk about here a little bit is some benchmark results that Luke Lonergan from GREENPLUM posted on the web. And he's basically comparing GREENPLUM single node edition, that's what SNE means, with POSTGRES. His interest, of course, is the fact that GREENPLUM is based on POSTGRES. So he wants to show that whatever they put on top of it is better than the vanilla POSTGRES. And now, he had a system basically with 8 cores, nice everything, 64 gigs of RAM, and 24 disks. And he actually benchmarked this with their own in-house benchmarking tool, and he was getting about 1.7 gigabytes per second linear scan throughput. Okay? Now, POSTGRES cannot really use multiple hard drives in parallel. It doesn't really know how to do that. And since in this particular setup, the 24 hard drives were grouped under 4 RAID controllers, only one of them was made available to POSTGRES. So the throughput on that was about 425 megabytes per second. Okay. Now, these numbers, why am I insisting on these numbers? Because we want to have these numbers in mind when we see the performance, just to see how all the numbers compare to some kind of linear scan over the data. Okay? Now, GREENPLUM, it's actually using column store, which is important, and compression. Okay? And if you use column store and compression, supposedly you're going to read a much smaller amount of data from line item compared to the 70% of all the data, right? So instead of reading for 1 terabyte instance, instead of reading 700 gigabytes, it's going to be more in the order of 200 to 300, even without compression. I know from our system. Okay. All right. So now, if you go on with the published numbers, right? The comparison at 100 gigabytes for query 1. I'm showing query 1 and query 6 here only. Right? You notice that GREENPLUM is doing 20 times better on query 1 than PostGRES, and about 10 times better on query 6 than PostGRES. Okay. Now, of course, why is GREENPLUM working better? Well, because they actually use all the 8 cores. PostGRES pretty much uses only 1 because of the architecture of the system, right? So they actually used also the hyperthreading, so they fired up 16, not 8 cores. Okay, so this is great news for GREENPLUM because their database is 10 to 20 times faster. Okay, but then Luke went on and benchmarked only GREENPLUM for 1 terabyte. And he didn't even bother to do PostGRES because the time would have been so way off, he basically gave up. And his running time for query 1 is about 1,800 seconds. And for query 6, 171. Now, this looks OK because he scaled linearly from here, but not if you look at the details. Right? So in particular, you computed that query 1 processes data only at 40 to 50 megabytes per second. This on a system that's capable of 1.7 gigabytes per second. Right? So you're basically running about 20 times slower than what you should be running given your I/O subsystem, which means you're severely CPU bounded. Okay? So there's no hope to do multi-queries or anything like that. Okay? And if you do some math, you realize that GREENPLUM spends about close to 30,000 clocks per tuple. Now, this is basically a disaster. That means you're doing an enormous amount of effort to process every single tuple. And a good number there would be something closer to 100. Well, an ideal number, well, remember, you have to do about 17 floating point operations. There's no hope you can do it less than, let's say, 20, 30 cycles. Let's say 100 because I'm allowing a little bit of leeway in there, but not 30,000, right? So we are off at least by a factor of 30 or more. Okay? And also, this suggests that GREENPLUM is actually slower than the linear scan, even on query 6, right? So the running time should be in the 60-second range on that kind of hardware, 60 to 90 seconds, depending on how they do things. But their running time is 171. That suggests that even those selection predicates in query 6 that don't look so complicated might actually create problems when it comes to fast data processing, right? They cannot really keep up with their fast disks in those setups as well. Now, this being the state of affairs, right, you can say, I'm going to get overly ambitious, and I'm going to set up some interesting goals, and then see what happens, right? So if you really want to design a large-scale analytical engine, here is kind of a wish list, right? You would like to, of course, to deal with queries that are 1 to 10 terabytes in size on a machine that's not more expensive than something like $100,000. Now, if you do this, if you do maybe some more work and you do parallelize it on multiple machines, you'll have chances to scale to petabytes within millions of dollars, which is more than acceptable, I think, for most people, right? Now, you want to focus, because that's where, as I suggested, the problem is, you want to focus on closing the gap between the theoretical CPU performance and the actual CPU performance. You want to get closer to that 100 cycles in query 1, okay? And not only that, but most of the time you want to be I/O bound. Even if you put very fast disk, a very capable I/O system, you want to be I/O bound and have room, if possible, for processing multiple queries in parallel. At 10 terabytes, right, even if I'm reading at 2 gigabytes per second, it's still going to take 10 minutes or something like that for, or a little bit more for query 1. There is room for running a number of them in parallel, especially if you do statistical analysis, right? Also, to address some big annoyances, right, you would like to have a system that doesn't really require a lot of tuning, stay away from indexing, not too much into all those tuning parameters, right? So now, how would something like this be possible? Well, if you have a very clean design based on linear scans, you might stand a chance if you stay away from all the other things. So basically, our answer to this is DataPath. And I have to mention from the beginning, DataPath is a complete system redesigned from ground up. Okay, we use almost nothing from pre-existing systems. And I'm going to, throughout the talk, I'm going to mention reasons why you might want to do this, why you don't really want to have too much ballast from previous systems. Okay. All right, so let me talk about two systems and actually some combinations around them. And this will give you also some kind of an idea of money, what money can buy, right? In terms of if you want a one system kind of capabilities. So from the NSF grant in 2008, spending about $60,000, we got basically a machine that has 8 processors, 32 cores, AMD. Only AMD can scale to 8 processors with reasonable money. 128 gigs of RAM. By the way, if you want to get to 128 gigs of RAM, you need these 8 processors. Because of the way things are now, the memory controllers are attached to the chips. There is no way to get 128 gigs of RAM without the number of processors and still stay at a reasonable price. Right? Now in the system, I'm using 2, actually in a version of it, 3 RAID controllers, and each of them get parts of the disks. Right? We used Velociraptor disks. We thought that was a good idea, and in the end it wasn't. They are overly expensive for what they need to do because you cannot even drive them so fast.
Why is it such a strange number at 47?
Because some of them failed. Okay, so I bought more, and they failed. That's what you get when you pay $300 for hard drive. Right? Now, if you actually benchmark this system, right, with just very low-level benchmarks, I managed to get about 2.2 gigabytes per second. Now, in other versions of it, I'm able to get a little bit more than that. Okay. Now, the new system, Chris somehow found some money. So he said, you have $20,000, buy something interesting. So the new system, which we just acquired about 2 weeks ago, has 4 processors, but 48 cores total, because this is the new Magni cores from AMD, right? So they have a 12-core chip. Also 128 gigs of memory. Now, by the way, this package is only $11,000, right? So some people complain we run on very advanced hardware. I would argue that $11,000 is not the end of the world, so we can afford it. And also, right, these two new hard drives that are capable of 1.4 gigabytes per second. Okay. Now, 1.4 times 2, at least theoretically, is 2.8 gigabytes per second. The question is, can I process that, or can I do something with that? I mean, it's still a very big if. You have to be careful when you look at specs coming from manufacturer. Okay. So before I go into details what DataPath does and how we actually do things, let me have a little bit of a discussion on why most of the other database systems are so slow, especially when it comes to heavy floating point operations, right? So why are we talking about 15,000 to 30,000 cycles per tuple? Okay. Now, if your system uses interpretation, then naturally things are going to be slow for many reasons. There are actually 2 things that go on in there. If you have an overly complicated representation of your tuple, especially if it's flexible, right? Just walking through that data structure, the processor is not going to be very happy. It's very, very hard to avoid killing the pipeline, right? Unpredictable behavior, it's never going to work quite as well. Also, if you walk through expression trees, it's the same kind of behavior, right? So these two things put together is going to make the processor basically just waste almost all the effort. Okay. But other things also come into play. For example, memory bandwidth is actually limited. In modern systems, memory bandwidth is the thing to watch because it's the hardest to actually improve. We had some improvement this year, but it's still kind of a big problem. Especially when you have a 48-core system, right? 48 cores will always kill any kind of arrangement unless you somehow map extremely well on the underlying hardware, NUMA or things like this, okay? All right, also latency is a very big problem. Now, this comes into play with traditional database systems in which computation drives access to the data. So if you say, oh, I need more tuples, by the time you push it all the way through the system, you pay for the latency to go through the entire memory hierarchy, possibly to the disk. Right? If you want to do things fast, things have to be there when you need them and not to wait for them. That's actually crucial to obtain very high throughputs. Okay? Now, let me just point out what modern hardware likes, because I think people don't realize just how severe the problem is. Okay? In some sense, the problem with the general purpose CPUs is that they allow any code to run on it. So you don't even realize that you're doing things inefficiently because you compile your code and it runs. You might even make it 2 times faster, but you don't know how fast it should be, right? But all of that predictable kind of hardware in the CPU is not really going to help for the most part to achieve more than, let's say, small factor improvements. If you want to actually have very streamlined processing, right, you must have very predictable memory accesses. This is the #1 thing, right? So it turns out that all the modern processors can detect both forwards and backwards linear access, either striped or not striped. Now you can ask the question, why backwards? because they changed the benchmarks a couple of years back, and they reversed the code to defeat the predictable behavior, and they promptly put hardware to detect the backwards one as well, which is great. So it gives you flexibility. Okay. Of course, benchmarks drive hardware. That's the way it goes, right? Now, why it's so good? Because this behavior is detected in hardware, and there is significant prefetching capabilities in the modern processors. For example, going from I think the L1 cache to the L2 cache, you can have 18 pending cache misses. And not only that, those are mostly going to be used by the prefetcher. When it sees linear access, it's going to, ahead of you, start filling in everything for the memory hierarchy. That's how you deliver data to the modern processors fast. Of course, if you have unpredictable memory access, all bets are off, and you pay full price for acquiring everything from memory. Okay. Also, modern processors like very little interruptions. Now, of course, they support all kinds of jumps and all kinds of things. That doesn't mean they like them. You can follow pointers. Again, that basically kills the pipelining behavior and so on. So what modern hardware likes is very long loops that have almost no data structures inside except arrays. And think about the fact that the GPUs right now basically ban pointers, and they only use arrays. Why do you think that's the case? Those people are obsessed about speed, and they want to keep the speed in the drivers no matter what. Probably they are going to put pointers in, and that's going to spoil the whole thing. Okay. Also, another issue is you want to have very little synchronization. The fact that the processors support synchronization doesn't mean is a very good thing to do. So on a NUMA architecture, synchronization is actually awful, because you really have to broadcast on all the buses and tell everybody, don't touch this thing because now I'm doing some atomic operation. Okay. It's extremely costly. It doesn't matter how you do it. Okay. That actually comes into play when you design the system, because if you have synchronization for every little thing, that's going to severely limit how fast you can actually do things. Okay. So if you have very asynchronous behavior in your system, you have much better chances to drive the hardware at full speed. Of course, it's not clear how you would design an engine like that. Okay. All right. Let's see. Okay, so I want to talk a little bit about a very interesting solution and contrast it to what we actually have done, and I'm going to describe later. And this is basically vectorized processing that comes from the MONETDB people with their X100 engine. I think they introduced it in 2005, right? And they have a very interesting idea. Okay? And it's potentially something that has chances to scale to terabytes and do processing very fast. And the idea is, well, I'm spending all the time on interpretation. Can I amortize the cost for interpretation? And the answer is yes, as long as you break your data into vectors. I'm going to have some slides to show how the dynamics of that happens. And instead of doing little things, I'm going to take this vector and do operations with vectors. So if I spread the cost over 1,000 size vectors, then the interpretation is suddenly not so bad. Okay. Now, they basically showed that they can get within a factor of 3 of handwritten code. Okay, that's much, much better than all the other engines out there if they don't use some special tricks. But here is kind of the kicker with this, is if this engine requires a vector algebra, which is not a big problem if you do only things that you do in SQL, because they've done it and they have the vector algebra, and that's what their research was all about. Okay, but it becomes a very problematic if you want, for example, to support user-defined code. A user has to be very sophisticated to write well-vectorized code. Users like to write simple things, right? This will not be able to actually use that and run at full speed, right? But this solution has a significant advantage even over column processing. So in column processing, the problem is you're wasting bandwidth. If I'm doing operations on entire columns, all intermediate results have to be written and read later from the disk. With complicated expressions, that's going to produce an enormous traffic to the memory, and that's going to be the bottleneck, and that's going to limit even your capability to do something like query one in TPCH. Okay. Now, vectors. Why are vectors going to help? Let me show this, right? So we want to evaluate this expression. We break it into vectors, right? So in order to do, for example, the first part of the operation, add A and B, I'm going to take this vector, and call a function that adds them up and produces this vector. Now, the size of the vector is such that intermediate results are going to live in the cache. If intermediate results are in the cache, I'm not producing noise on the memory bus, right? I'm not paying bandwidth for it. Whatever a processor does to L1 cache or L2 cache now, because L2 cache is independent for all the processors, right? It's internal affair. Everything beyond L2 cache means you're going to globally kill everything. Okay. So So this is what the MONETDB people did. They benchmarked their system depending on the vector size, and they realized that a good vector size is about 1,000 for the kind of caches you're talking about. Now, since the cache size doesn't increase dramatically, that basically means you're going to stay roughly there for a long time, right? So the intermediate results now, for example, I can do the division by RC, another intermediate result, combine the intermediate results. None of this produces memory traffic, right? So clearly, if you look at the X100, right, interpretation overhead is gone, because I amortized over 1,000 and it's hidden. Also, data access latency is gone if you play your cards right. The reason is you do extremely predictable memory accesses. You're scanning linearly the independent columns. You're partitioning them into vectors. That's kind of, anyway, just virtual. The only thing is make sure that the vector size is small enough to fit in cache. So the work size, it's small, right? And that's the only thing. Also, memory bandwidth is kind of taken care of to a large extent. It's kept under control, right? Because all the intermediate results fit in cache. I'm not producing noise on the memory bus. Okay? But what happens if I want to run multiple queries? I mean, one of the goals of what we want to do is be able to run multiple queries. And in particular, our problem is going to be not to be bandwidth starved at multiple queries. That's a very big issue. Right? So let's see what happens if I have 2 queries now in parallel. So if I'm running 2 queries in parallel, well, it turns out that I'm really not going to share much between the queries, which means the size of the intermediate results is going to grow. Right? So inevitably now I need enough space to do all the intermediate results for both queries in parallel, right? And that can actually grow to quite a lot. So if you're shooting for something like 10 to 20 queries, you have to do vectors of very small size to fit everything in cache. But small size increases significantly the time, because now suddenly the interpretation cost is spread over a much smaller size for the vector. Now, is it possible? It's probably possible, but it doesn't necessarily look like something that's going to be an easy game to play. Okay? So you might as well rethink it and try to do something new. So in the end, the MONETDB, it's a fantastic approach, right? As long as you do one query and you don't have user-defined aggregates, but has all these problems that I actually talked about. Okay. Also, I mean, MONETDB has another problem, which is they don't have a good I/O system. They pretty much say, I'm going to fit it in memory and deal with it, which limits you to tens, maybe hundreds of gigabytes. But there is no hope you're going to scale beyond that. And I mean, their published numbers show that, right? That they struggle significantly with the I/O. It's not so easy to make the transition from an in-memory database system to an out-of-memory database system. You really have to coordinate that linear scan with the rest. I mean, you cannot just put it on top of it and hope it's going to work, right? So let me just give you some kind of an idea from the numbers published by the MONETDB people, what kind of performance they got to see just how good X100 is versus PostGRES, right? So this is on a 4-core machine with 8 gigs of RAM and 2 hard drives. My estimate is that the 2 hard drives together should be able to do between 100 and 200 megabytes per second throughput. Okay? So I mean, if you look at query 1 performance, for 1 gigabyte, I need about 1 second. It goes up to 40 seconds for 10 gigabytes, because they start to spill on the hard drive here, and actually the hard drive becomes the problem. And indeed, they're much faster than PostGRES or MySQL with the X100 engine. Okay. Now, interestingly, PostGRES, right? For example, for 2 gigabytes, PostGRES runs in 76 seconds on this kind of a CPU. I'm going to come back to this number later when I talk about DataPath running at 1 terabyte. Okay. And even, right, so if you compare with what I think the linear scan should be able to do if you have no CPU bottlenecks, both PostGRES and MySQL are definitely severely CPU bound. Okay. Now, interesting, that's happening also for query 6, not only for query 1, because of those attributes. Okay. All right, so let me try to get closer to DataPath and talk a little bit about the kind of underlying philosophy when we designed the system. Okay. So really, we wanted to do something that we called data-centric processing, not compute-centric processing. Right? So in compute-centric processing, the idea is my CPU is so much faster than the disk. I'm going to ignore all the latencies. I'm just going to go on and ask for the data only when it's needed. This is pretty much all the database systems out there, with some exceptions. Okay. Now, the problem with the compute-centric is, if you run a single query, right, it's very hard to anticipate the data need, especially because it's usually paired with indices and other things. Right? That basically means all bets are off. You have to wait for the computation to tell you what you need. You can try to detect linear scans and try to do something in there, right? But it's not going to necessarily work as well as it should. Right? So you have to pay for the data latency. Now, there is something else, even though you could argue a little bit in the other direction, which is there is really no clean, natural way to coordinate data requests among different queries if you want to do multi-query processing. Right? Now, definitely the disk is fast, but not so fast that I can do completely independent data pathways because I'm going to spread my bandwidth over multiple queries. The goal would be, can I design a system that when I run multiple queries, it takes about the same time as running one query? If you do that, then you have a great system. Then you can actually do interesting things. Okay? Now, so if you take a data-centric approach, the idea is going to be, now data is important, and moving data around is going to be the major cost and the major consideration, right? Then I can have data have a mind of its own. I'm just going to latch computation on it. Now, if you start to be concerned about the data, what you would like to do is, when you get your hands throughout the memory hierarchy on any tuple, you would like to do as much processing on that tuple as possible, right? So that you're not going to incur any extra memory bandwidth cost once you acquire the data. Now, how you do that, it's still you still have to think about this, right? But if you do a data-centric system, it should allow you to do extremely aggressive prefetching. I'm ahead of time. I know what I need to do. I'm just going to create a large pipe. I'm just going to throw stuff into your system. Okay. So effectively, what's happening is you have all orderly data pathways that form. Now, something that people don't realize is you really need to get in quasi-stable regimes in the modern hardware. If you can get into oscillating behaviors that actually completely kill performance. So let me give you an example. The IBM system, the $11 million IBM system that sits on top of the TPCH 10 terabyte, right? When it runs multiple instances of query 1, it runs slower than running the query sequentially. So that basically what it means is it's faster to run 9 queries one after another and add up the time than to run 9 queries simultaneously. They lose about 30% of the performance. That basically means that the queries are just fighting with each other and pushing the hardware in weird ways and losing performance over completely sequential execution. Actually, the best you see, especially at 10 terabytes for TPCH, is not to lose time versus doing one after another. Right? So I know SQL Server doesn't lose time. It just adds up. But IBM tends to lose time because they probably were very aggressive with some of the things inside. Right? So it's very important to have this kind of very large pathways in which you do things in order if you want to achieve peak performance. Okay. Now, there is something interesting here, kind of psychological. Once you focus on the data and you're going to say, I'm going to push the data no matter what, right? You're forced to come up with very innovative ideas of how you're going to process it because otherwise, right, you cannot even put this on a slide and say, I read from the disk at 2 gigabytes, but I process at 200 megabytes, right? You have to keep up. So you're forced to come up with interesting ideas to keep up. It helped us tremendously, right? Right, so, I mean, what's going to be the DataPath execution model? Well, I talked about X100 is vectorized processing. The idea in MONETDB was stay away from tuple processing because you have large overhead for interpretation. Right? Now, we decided actually to do a tuple-oriented execution model in DataPath to overcome the problems that X11 has, which is the cache puts a limit on how many things you can run in parallel. Okay? Now, definitely if I do one tuple at a time, intermediate results are going to be much smaller. So I should be able to do a large number of queries in parallel. But the problem is, of course, how do I get around that interpretation? And it's going to be later on the slides. We are basically going to generate some special code on the fly, compile it, and run it. Okay? I'm going to have to say a lot more about that. Okay? But the idea is, it's not only that. It's throughout the system, I want to do as much sharing as possible. And I don't want to share computation. I want to share access to the data. The expensive thing is access to the data, not computation. Modern CPUs have enormous capabilities in terms of floating point performance. There is room to do all kinds of computation in there. It's getting the data from the memory that's kind of constricted. Okay? Now, I'll have many slides on this. The data is organized into chunks that are going to be processed by waypoints. But the interesting thing that's going to happen is whenever we do any processing on the data, we are going to have this kind of loops go for a very long time, about 2 million times, and say, does this tuple belong to query 1? Yes, do processing for query. Belongs to query 2, do processing for query 2. What this means is the queries now are inside. Right? I access the tuple. I do processing for all the queries that need the tuple at that point, as opposed to having independent query plans. Actually, so one interesting idea would be I can afford to do independent query plans as long as I have shared scans. You have lots of papers published about this, right? I'm going to have a slide by the end to convince you that on my benchmark system, you can do about 2 queries in parallel if you read very fast from the hard drives, and then your memory bandwidth starts. Right? If I read at about 2 gigabytes, close to 2 gigabytes per second, my overall memory bandwidth across the system in that system was about 6. If I split the data, I can split it in 2. Okay. Now, for very fast reads from the disk, and that's what I have my eyes on, you have to be very, very careful what you do with the data. You cannot even look at the data, because looking at the data, you pay bandwidth for it. Right? So you have to do a lot of things by not looking at the data. Right? All right, so we'll see in a second how that works. So let me run through an example to give you an idea of exactly what I'm going to share in terms of computation or data access or whatever is going to happen there. Right? So this is a simple query on line item. Right? I have a selection and an aggregate. And this looks like a traditional plan. Right? I'm going to read from line item, filtering condition on the ship date, and then an aggregate, and then some kind of an output. Okay? Now here comes the second query. This is a join between line item and orders. Right? Now, when I'm trying to execute this query, I could consolidate the filtering condition that I have to do on line item into a single place. The advantage of that is going to be once I acquire the tuples, as long as I deal with that avoiding interpretation, I can look once at the tuple and then process both predicates in there. Okay? So interestingly, I'm not so much interested in shared sub-expressions. I'm interested in shared access to the data. Right? That makes all the difference, as you'll see. Now, if I have a third query that's very similar to the second query, it's even hard to see where the third query is because it's interspersed. I just added information to this so-called waypoints. Right? So I'm just asking them to do a little bit more. Potentially, there is room to do a little bit more as long as I avoid the interpretation because there is enough CPU to go around, especially if you have 48 cores. Okay? All right, so let's focus a little bit on that tuple processing loop because that is one of the critical things in DataPath. Right? So how are we going to avoid the usual problems with the tuple processing? Right? So for example, Chris was telling me when he gave a talk on this, Mike Stonebreaker was in the room. And as he was describing the system, Mike said, but tuple processing is inefficient. Right? So I want to convince you that you can get tuple processing to be very efficient. And the way to do that is to use a C++ meta compiler. So the idea is I'm going to start with a SQL description, find a way to break things into those waypoints. Who needs what access to the data? But once I figure out what computation needs to be done in every point on the data, I can generate on the fly good quality C++ code. Hopefully, I'm going to show you some of that code and convince you it's good quality. That the compilers like, and then throw an optimizing compiler at it with the best optimization options. Right? As you will see, everything is hard-coded, and the code that results from this is very fast. Okay? So, for example, on query 6, by mistake, I discovered that the difference between optimized and non-optimized code with -03 is a factor of 23. Usually, you expect a factor of 2 or 3. Right? Especially when you have multiple.
One question.
Yes?
When you say that you're going to compile, the fact that Q1, Q6, and Q9 are going to run together is not observed at runtime, but observed at compile time?
Right, so this is the way we can actually do things. Right? We can do things also incrementally. Right? So say the system was running one copy of query 1, and now another copy of query 1 comes. What I can do is basically say, oh, let's generate code now that does both, and switch with the new code on the fly. A lot of the headaches in the system were related to this. How do I switch on the fly and make sure I don't do work I shouldn't, or I don't miss work that I should do? Okay, but it's doable. Okay. Now, you can do other tricks. For example, query admission. Right? For example, you can say, I'm going to allow on a 10 terabyte instance, I'm going to allow queries only every 10 seconds. So I'm going to accumulate queries for 10 seconds because anyway, you're going to run 1,000 seconds on them. Right? So there are lots of things you can do that are kind of common sense that will alleviate maybe the need to compile so much. But the compilation can actually save tremendous effort in overall, especially at 10 terabytes. Now, an interesting thing, if I do this, is I put the compiler to do all the ugly work. For example, finding shared sub-expressions, all that stuff. And the compiler knows how to do that very well. Okay. And also, to match things extremely well on the underlying hardware. It's actually packing things into SSE instructions. I mean, really running them at the peak of what you could do even by hand. So the idea is the code generated to look exactly like what a very good programmer would do if he would ignore anything about data structures and just try to get the job done. Okay. So a critical part in the system are the chunks. And I need to talk about them because it really, the whole system revolves around these chunks, and it's important to have a good starting point. Okay. So now what these chunks are, really, they are both the unit of execution and the unit of I/O. Okay. They're bundles of about 2 million tuples. Okay. And the idea is to have something in between column processing and traditional systems. So the problem in column processing is the columns themselves are too large. And then you're forced to do all that stuff with the columns. Now the chunks are small enough so I could get the nice behavior. And also it's very important to have some kind of unit of execution because I want to avoid synchronization. And if I have chunks and say each core will run about 1 second per chunk, I can still talk about who does what work and how I distribute it at the chunk level. Okay. So a lot of thinking went into designing this kind of chunks. Okay. Now I'm going to dive into the diagram and explain what various parts do for the system and explain what the implication is when it comes to achieving speed. Right? So the chunks are the key for the speed together with the code generated. Okay? So the first part here is going to be this bitmap. So the idea is the chunks contain data, and the data is really designed for multiple queries. I need to keep track of what query cares about it or not. For example, when I do a selection, I start maybe initially with all the bits on 1, all the queries care about them, and I'm going to turn those bits off. Right? So why are we doing this? If you want to reorganize the data, you pay memory bandwidth for it. We have to avoid paying memory bandwidth at any cost. So if the selection could only turn on and off some bits and not, for example, reorganize completely the tuples, that's a tremendous help right there. Okay? So those bitmaps are going to help. Right? And interestingly, we can read data from the disk so fast, I'm going to describe this later, that even writing these initial bitmaps has to be done in a multi-threaded way. Because one CPU cannot write the bitmaps as fast as the disk can bring the data in the chunk. Now another interesting part about the chunks is all my columns, right, are going to be arrays in memory, contiguous arrays in memory, stored column by column. Okay. Now why is this important? Because say at this point I need to access only 2 of the columns. I'm not going to even bring them through the memory hierarchy if I don't touch them, right? So if I'm using only this column and this column, the fact that I have these columns, it's immaterial because the processor is not going to look at them at all, right? So while I do the processing, I'm just getting access to the columns I actually need and scanning only the columns I need. So it doesn't matter what the total size of the chunk is. What matters is how much of it I actually access. Okay. Now you have metadata information in the chunks that allows you to deal with the chunks routing around. But the fact that the system is data-centric means we have to be ready for the possibility that the computation cannot keep up with the I/O. Now, the way to do that is to have some mechanism to say, I couldn't keep up and kill some of the data and produce it in the future. So we have a kill mechanism. You say, kill this chunk, which basically means the bottom part is going to produce it again in the future. Even dealing with this nicely so you're not creating problems was kind of an interesting, challenging problem. Okay. Now, also, the chunks are going to have a universal schema. And since I can put basically null pointers for the things that are not occupied, I'm not going to use much of the space. Now, a universal schema is going to be awful if you do it at the tuple level. But if I do it at the 2 million tuple levels, it's not going to be a big problem. Now, why do we have universal schema? Because you actually create significant problems when you run multiple queries in parallel. A query needs some attributes, another query needs some attributes. You have an exponential number of possible schemas that could happen there depending on when queries got injected. It's madness unless you do something like this. I mean, that's what we realized. Okay, it's a nice, elegant solution for it.
The universal schema is a logical assumption, not materialist.
Of course, of course. So logically, basically, you'll allocate slots for all the things you might need in the system, and you map them or don't map them. It's bookkeeping. Okay. Now, yes.
Does the notion of chunk only apply to base relations, or does it also happen for intermediate?
Right. Fantastic question. So actually, the chunks apply throughout the system. We insisted on, even after a join, of course, when you do a join, you're going to have to do something else. You cannot keep the chunk. You have to do some hashes. But when you pull stuff out of the hash, you're going to make it a chunk again. The reason is, again, things are stored by columns. So that's a very good thing for the whole memory hierarchy. You're going to access only what you need. Okay, that's important. Now, another thing is the following. Is we keep these reference counts for each of the columns, and that allows us basically to strip columns and just reattach them to other chunks, or to basically do shallow copies of chunks. Now, this is actually critical because eventually you're going to have to send data to 2 different places. You never ever want to copy in a system like this, right? Because copying, it requires tremendous memory bandwidth that basically kills performance. Okay, so the way to do that is basically through this kind of reference counts. Okay. So really our approach when we design the system is to have a zero copy system. Try to avoid copying at any cost. If you can put some data structures around it to just flip some pointers and get it done, do something like that. We can do it because we store 2 million tuples in every chunk, right? So it doesn't matter how complicated the mechanism is. I do it for 2 million tuples. You don't really care. So we didn't have to be paranoid about how we do any of this stuff. Okay, so an interesting question is, okay, so how do you design a fast linear scan? Okay, and it turns out to be non-trivial, especially if you really, really want to push it to the limit, right? So one of the least understood things is the page sizes when you read from the disk have to be large, right? So we just bought those $100 hard drive that do 150 megabytes per second. Well, it turns out that if you don't have pages at least 32 kilo in size, you're actually, the difference between a 32 kilo page and a 4 kilo page is a factor of 4. You're losing it because you have the page too small. And that's because of the controller on the disk. Okay. Now, of course, if you're going to skip things, so by the way, when we read chunks from the disk, if nobody needs particular columns, I'm not going to read them. I read only the columns that I need, which means I'm going to do a little bit of skipping around when I read from the hard drive. It's not going to be perfectly contiguous. So you really, the page size should be closer to half a meg to a meg if you do skips in order to amortize the seek time. Okay. Now, interestingly, for these OCZ drives, I benchmark them. If you don't use a 4 megabyte page, then you're not achieving maximum throughput. The difference between a 4 kilo page and a 4 megabyte page is a factor of 50. Okay. Now, you might ask, why is that the case? Well, basically, the way they achieve that enormous throughput is by asking all the different memory chips in parallel with a RAID 0 system to read. Right? Now, that actually creates interesting problems. Right? So if you want to design a fast linear scan, eventually you have to talk to the operating system. Right? And operating systems are not necessarily ready for throughputs of this kind. Or they don't necessarily know that you might have things aligned on a 32 kilo at least page boundary. Right? So if you want to get fast scans, you must use direct I/O. Because, I mean, caching is not useful if you do linear scans. You promptly throw away whatever you read. Okay? You're just wasting memory bandwidth. Okay? But also, alignment is very important, right? So even in the buffers that you read in memory, they have to be 4 kilo aligned, because otherwise the operating system is forced to do a copy, which basically means I kill a third of your bandwidth. So you can lose half the performance by not being careful when you align things. Okay? It's critical to use DMA transfers. Right? It's critical that nothing gets copied anywhere. The DMA controller that talks to the hard drive dumps things directly where they should be, and things just magically appear there. Okay? An even bigger problem is the fact that the file system and the partitions are in the way. And it's not clear why the partitions are in the way. I'll explain in a second. So the file system, first of all, uses pages that are too small. Right? So that's a problem. But the partitions it's something that I just realized when I tried to create 2 partitions on these OCZ hard drives, and I couldn't get more than half the bandwidth from any of the partitions. So I got 1.4 gigabytes if I read the whole disk, and only 700 and something if I read the partition. And then it crossed my mind what the problem is. Well, the problem is I need large pages, which are 4 meg pages. If I create a partition, a little block is going to be at the beginning, then the partition is going to start misaligned. So my 4 meg requests will require 2 of those physical 4 meg pages, which basically halves the bandwidth. I mean, these are all little things that matter a lot when it comes to getting the performance. Okay? And also, you would like to have as much asynchronicity as possible in the system, right? If anybody waits for anybody and you don't delay the waiting as much as possible, you will slow things down. And that goes with the CPU and goes with the hard drives. Hiccups happen all the time. I mean, if I'm going to do that many requests simultaneously, a hard drive is going to have little hiccups every now and then. You don't want to slow down the system only for that, right? So really, the way the chunks are constructed from the disk is the pages start on the disk, and then I'm going to have a staging area in which I build in parallel chunks. So again, this is about getting high throughput. A chunk doesn't have enough data to even keep my hard drives busy. I'm going to show you hopefully a demo with 50 hard drives, right? If you have 50 hard drives, unless you have tiny pages which are not desirable, even constructing one chunk at a time is going to limit how much you read. Okay, you need a large staging area, right? How large? Well, ours is usually around 10, okay, for line item. Okay, so as pages are read from the disk asynchronously, you start filling in things. At some point, right, chunk 1 has all the pages, but the system doesn't know yet. Then it discovers later, throws it into the system, and replaces it with the chunk 5 that now needs more pages, right? I'm going to show a system diagram to explain how this dancing is happening, right? And you keep on going until you get your chunks, okay? Now, let me briefly talk, it looks like I have to speed up, briefly talk about the DataPath execution engine. Okay, so the execution engine is really responsible for getting those chunks from the I/O and taking care of all the computation that needs to be done and eventually finishing something. Okay. Now, I mentioned the fact that DataPath is push-based, so things come from the file scanner without no control from the execution engine. And if execution engine cannot keep up, it's going to send this negative acknowledgement, say, I had to drop this, produce it in the future. Even intermediate results can actually be dropped. Okay. Now, inside the system, because we have the chunks, right, we could separate the deciding what you do with a chunk and what computation needs to be done on the chunk and the actual work. Right? So the execution engine is going to have these workers around. The workers only get an abstract class, a class that has a run method and just run them. But we're going to have a different kind of code that's in the waypoints deciding what work needs to be done. Okay? And that depends on how you actually write them. Okay? And the execution engine is going to have to take care of all the chunks floating around in the system, routing them, assigning them to workers, asking waypoints what needs to be done, and deal with them coming from the disk. Okay, so this is an overall system diagram. And I want to mention that I'm going to zoom in on parts, so don't necessarily read what you see in there. But I want to mention that every little box in here corresponds to a piece of the code. Actually, we implemented something that's similar to the actor model, and we call them event processors. So they are really independent threads that exchange messages to talk to each other. And all of those arrows are actually messages that actually go around. Okay. That was a tremendous save in terms of designing the whole software, right? We spent 3 days writing this little framework, and that probably saved many months in designing the rest of the code. So let me zoom in on the bottom part first and explain you how the data is acquired from the disk. So I have my disks here. They're going to be controlled by these HD threads, which are independent actors, right? And these HD threads somehow are told, you have to read this page from your own disk into this memory location. Now, you do some bookkeeping, and you have an idea of mega jobs related to chunks. The last guy that reads the last piece from a chunk is going to send a message to this intermediate thing. You don't want to have too many messages going around, so you try to cheat here and there. Now, the way we are going to talk about pages over the entire disk array, which potentially has 50 hard drives, right, is we are going to have a flat view of all the pages. On all the hard drives, all the pages have the same size. In my system, it's going to be either 1 megabyte or 4 megabytes, depending on what hard drive I use. And this guy is responsible for breaking high-level requests into independent requests for the hard drives. Now, in a previous version of the system, we actually had this subsystem for each relation independently. But it turns out that the operating system got dizzied up, so we had to centralize it and have a single place where you go to the disk. Now, this guy is actually going to use a striping function to spread all the pages over all the hard drives. You do that when you bulk load. You do that when you read. And I have there a nice striping function that actually has very uniform load balancing on all the hard drives. That's kind of the best behavior. And I try to make it independent of whatever columns you read or you don't read. Any uniformity in here potentially will lead to some kinds of resonant behavior, which is not very good. Okay. Luckily, it wasn't a hard problem. Now, how does this guy know what to read? Well, the file scanner is responsible for getting chunks from a relation. Okay. It's going to have that staging area. It's going to send multiple requests to this intermediate guy that's responsible for taking care of all the little details. And this guy has to be multi-threaded because this guy is responsible for doing the bitmaps. Okay. Which in turn is going to send requests to the disk array. Okay. And this is going to happen at very, very high speed. Yeah, I'm going to show you numbers. Of course, the same thing for the other relations. Now, the top part, right, this is my execution engine, is going to get full chunks from the file scanners, completely asynchronous, coming from all of them, so it has to deal with them. And also, part of the execution engine is going to be that code that deals with the waypoints. So when it gets a chunk, it says, oh, I have to route it to the join. I have to ask the join what to do with it, because I don't know exactly what it wants to do with it. And you come back with so-called work units, and then you schedule them on one of the workers. If you don't have enough workers, you decide to drop the chunks, just to not overflow the system. Okay. These workers basically are going to correspond to my cores. For joins, it's better to have about 2 per core, it turns out. For the other processing, about 1 per core. Even if you overbook by 2 per core, you're perfectly fine. Okay. Now, usually when you run queries, you only stay below this line. When you inject queries, you have to talk about the top part. So we are going to have some external program that's the optimizer, does some kind of planning. Right? It's going to tell this guy, the coordinator, oh, you need this to inject the query. Things would need to be processed, and code needs to be generated, loaded on the fly. And then you tell the execution engine, by the way, this is the new code that you have to switch over to.
which unit is dependent is in charge of keeping track of what parts of a query have been computed and so on?
Execution engine.
Okay, so it does all the bookkeeping.
Yes. All right. Looks like I have to speed up. Now, implementing those waypoints, the thing you have to insist on if you want to keep up with those very, very fast linear scans is everything has to be multi-threaded. Right? So you might think that selection is easy. I can afford to have only one thread. It's not true. Actually, query 6 requires multiple threads even for one query. You need that 1.5 cores to run to keep up with the disk, even for query 6. Even if you generate code. I'm talking about generated code, not about interpreted code. Okay. I talked about the execution units. I'm not going to talk about how we implemented most of the waypoints except the join very, very briefly. Right? So the join is very interesting in DataPath. Okay, so the current implementation is only an in-memory implementation. We're working on an external memory implementation. We designed it for the worst case, namely line item and orders. 2 enormous tables. How do you survive that? Okay, and really what we wanted to do is to make sure that, so this is an asymmetric hash join. I'm going to build a hash on the smaller relation, and I'm going to probe on the large relation. We wanted to make sure that while you do the probing, you have no locking whatsoever. I mentioned the fact locking is not, it's something that's going to slow down the things, right? So we want to make sure while we do the probing from the left side, we have to do, we don't have to acquire locks to individual, let's say, hash buckets. Now, the way we are going to do that and still keep correctness is we're going to use some locks when we build the hashes, but we are not going to ever do simultaneously both probing and building the hash, right? So you basically stop temporarily the probing, the building, and you do the probing. Right? It's a complicated dance. Right? It took many months to get this perfected. Okay? Also, we are not going to insist on overly smart solutions. We can afford to do one random memory access per lookup because we should be able, with so many cores, to achieve about 100 million lookups. And indeed, in the system that we have, we do about 110 million lookups per second. So it's fine to have that cost, but as long as you do one random memory access. Okay? And also, I have some ideas about how to use the work of Natasha Elemahi, how to do prefetching, in order to maybe squeeze a little bit more performance in there. Okay. Also, the join is going to use a so-called one large hash table. Right? You're going to put data into a single large hash table for all the queries simultaneously in there. That solves a lot of your problems, but also introduces other headaches. Right? So, for example, you're never concerned that you have to reorganize the hash because suddenly it's larger than you thought it is. If the large hash is not enough, you basically have to give up or start doing some external algorithm. Okay. The disadvantage is concurrency control tends to be very complicated, but it's confined. You can keep it under control. Okay. Also, we use the following kind of strategy. We build smaller hashes and integrate them into the large hash, so we don't have to lock the large hash even when we do the probing. Remember, we do things in parallel. I'm going to have 32 threads that build stuff, right? So you have to be careful even how you do that. Okay. Now, so basically, in order to insert things into in the interest of time, I'm gonna skip this because I'm running out of time. But it's basically you're just finding room in the hash and you inject your tuples when you do the building and when you do the probing. Depending on what you find or you don't find, you have to eventually get to the point where I found the tuple. I'm gonna do the join. Okay, it's somewhat complicated, but not overly complicated. Okay, now at this point, since I don't have much time left, let me switch over and at least start one of the mini benchmarks with query 1. I'm going to start it on 10 terabytes and try to do one query 1 on 10 terabytes. And at the same time, I'm going to play with a 1 terabyte instance. I have 2 machines now. 1 terabyte instance, and then I'm going to try multiple queries on 1 terabyte. Okay, and then I'll come back to this. So let's see how this is going to work. Okay, and not only I'm going to run the system, but I want to see kind of what the performance of the system is. Right? I'm going to show you with IO stats how much am I reading from the hard drives. And also, let me actually start the whole thing. Right? Before the talk, I told this guy, this is a special executable. I told this guy, run only one instance of query 1. It's already prepared in some intermediate files. So I'm starting this. Right? So it tells me that it took 1.44 seconds to compile the whole code, injecting into the system. Now those dots that you see in there, all of them are a chunk process, 2 million tuples processed. Okay? If you see an X there, that means I have to drop a chunk. So no X's is good news. Okay? So let me now pick and see what kind of I/O am I getting. Right? So I have I/O stats here running, right? And you see my 50 hard drives, and I have 50 hard drives. So a speed of 50 something is 50 times 50. It's 2.5 gigabytes per second. Sometimes it does even something closer to 58. Now don't ask me why. Sometimes it's a little bit slower. Sometimes it's a little bit harder. This is complicated hardware, so I don't know. But it looks like we are processing data at a healthy pace, about 2.5 to 2.8 gigabytes per second. And it turns out that we can finish query 1 on 10 terabytes in below 1,000 seconds. I think the latest number I got on this was closer to 600 seconds, right? Which is definitely in line with one query performance with all those $1 million systems on published TPCH results. Okay. Now I'm going to show you multi-query processing. I'm going to let this guy run. And so an interesting thing, by the way, is the fact that I'm using only about 8% of all the CPUs to run one query one. That's because of all the query compilation. Okay. There is room CPU-wise to run a lot more than that. Okay, it looks like I'm not in the right place. Right, so I'm going to do query 1, and let me do something more ambitious, something like 8 parallel instances of query 1. I have a script that generates the configuration files for 8 of them in parallel.
What did you say, 8 instances of query 1?
Yes, independent instances. All of them have different selection predicate. And I have to filter most of the output because otherwise it's going to get slowed down by displaying things on the screen. So, okay. So again, we see exactly the same kind of behavior. It's compiling them. It takes longer to compile a query, so it took 3.7 seconds. And let me peek at the performance here. It's probably going to finish by the time I'm done with IO stats, right? So it needs 5 seconds to refresh properly. So you see I'm reading at 1.2 gigabytes per second per hard drive. That's 2.4 for the 2 OCZ hard drives. Okay, that's kind of a pretty good speed. And you see the dots basically just flying and no chunks dropped. I'm going to put some large number there to show you that it actually drops chunks if you cannot keep up. Okay, and we're going to see what the running time is, right? So, right in the meantime, you see various kind of speeds, but sometimes even the 10 gigabyte instance gets up to 56, which puts me at about 2.8 gigabytes per second. Okay, so again, what's happening behind the scenes is the SQL for the query 1 gets compiled into that C++ code, gets loaded on the fly. I have only one instance here, right? So you see the running time is about 70 seconds for all the 8 instances of query 1. It's kind of weird, but right? So let me try something a lot more ambitious, which is let's put 32 query 1s. And you're going to see the compilation time goes higher. Actually, there is an interesting thing in there. When I tried 90 queries once, the Intel compiler spent 47 minutes compiling the code. The reason is the compiler people are not ready for this because they've never seen for loops that are so large with code inline with so many opportunities to do optimization. So I noticed that it built a data structure of 3.2 gigabytes and was probably doing flow analysis on it to try to find the very best way to run it. And of course, it takes only about 10 minutes at 10 terabytes to run all those queries, right? So it's kind of, so you see now, the system is overloaded, it has to drop chunks. The chunks are going to get produced in the future. But it's surprising, even at 32 queries, that I'm not just having drops everywhere, right? So the system pretty much keeps up to about 15 queries. Things slow down a little bit, yes?
So if you drop a whole bunch of chunks, do you have an intelligent way to re-scan just those kind of chunks?
Of course. So I mean, what's happening is, it's very easy to be intelligent here because the chunks are 2 million in size. So I have basically a nice bitmap that I keep for every chunk times query, right? So when I push a chunk in the system, I zero out my bitmap. When it gets dropped, I put it again at 1. I scan and I look, anybody needs this? Yes, that's how I'm going to stamp the scan.
But you don't use random seeks? You don't use random seeks at all?
You always tend to go in a big circle. It doesn't matter if you use small jumps. On the OCZs, for example, it doesn't make any difference if you do random jumps or not, as long as you have 4 meg pages. Right. On the other hard drives, matters a little bit, but it's not the critical factor because pages are so large, they're 1 megabyte in size. Okay, let me switch to my talk. Right, so we are talking about running times on 1 terabyte around 70 seconds. Remember that Postgres for 2 gigabytes was doing about 70 seconds, right? And Postgres is completely incapable of using multiple hard drives simultaneously, incapable of using too many CPUs simultaneously, at least the older versions, right? So even on this machine, it's going to run comparably. So that's a gap of about 500 for one query, and we can run about 15 queries in parallel. That's already a 2,000 gap, which basically suggests that we can go down from that 30,000 cycles per tuple if I do multi-query processing much, much closer to 100 queries, clocks per tuple. Okay. I'm not going to talk about how you come up with, how you map things into multiple, how you take multiple queries and map them onto the same network structure. It's a very interesting problem, mostly because you have a lot more opportunities than in traditional multi-query optimization. You don't need any common sub-expression. All you need is the same access to the data. Okay, so then you have a lot more opportunities. That doesn't necessarily mean it's not a hard problem, right? So interesting theory to be done here, I guess. Even the cost model has to change because you're really concerned about memory bandwidth, not about the number of disk I/O. So it's not clear how you would change that. So let me mention a little bit more about the kind of numbers we got. You already have seen some of it running, right? Especially what I want to show is numbers for running a diverse set of queries, right? So not only query 1, query 6 is not so interesting, but queries that have lots of joins in them. So we basically, since we don't have a general group by implemented, we took a subset, we crafted some TPCH-like queries that don't have group bys. We made sure there is absolutely no sub-expression whatsoever because we wanted to actually test the system. And so no opportunity for traditional multi-query optimization. And we basically have 8 independent queries. The 8th one is query 1. And 7 of them involve line items. 6 of them have joins. Some of them are atrocious joins, line item of orders with almost no selection on orders. Okay, so I'm going to show you what kind of things we get if we run every query in isolation, then groups of free queries with shuffling. So it turns out that the optimization problem we have, we don't have a fantastic solution. So if you change the order in which you see the queries, you get different plans and they have different behavior. Okay, and the same thing for 8 queries if you change the order. Okay, and 8 concurrent queries for TPCH. So this is 1 terabyte results, right? So these are the running times. Now there is something interesting happening in here. The queries have running times that are very close to each other. This is running time in isolation. And the reason is you're relying on those linear scans. Almost all the time you end up scanning line item, and that's most of the cost. And this is why the cost for all the queries, it's going to be very close within a relatively small factor. Okay. All of these queries are basically just I/O bound. You need a lot of queries in the system, like you've seen 16 instances, 32 instances of query 1 to actually get to the CPU bound part, or very heavyweight joins. Okay, the total serial running time, it's about 609 seconds. So look what's happening if I run now free queries, groups of free queries, right? So the running time, of course, goes a little bit higher, but not much higher. You're still reasonably close to this query 5. But running multiple instances of query 1 in TPCH, right, stays roughly the same. And this is the interesting thing I want to spend some time on. If I take now 3 different orderings of the 8 queries and I push them through my optimizer, I get 3 different plans. One of the plans is very good. The running time is 281 seconds. Remember, no sharing in terms of sub-expressions here at all. So running time is 281 seconds versus the 609 seconds. But it turns out that some of the plans are not so good. And it's very hard to tell the difference between a good plan and a bad plan. Right? So this plan, for example, in the paper we had at Sigmod, we have a nice explanation about that. Right? The difference between this plan and this plan is you start doing some, building some hashes too early. And that bogs down the whole system. Doing the building part of a join turns out to be a very traumatic experience for the whole system. The system is basically paralyzed just doing the probing, just doing the build. When you do the probing, you're okay. We can actually keep up with 110 million tuples per second when you do the probing, but not when you do the building. The building involves all that complicated stuff with put stuff in the hashes and so on and so forth, right? All right, so I made already this point. So let me remind you again that the HP Superdome takes 142 seconds for query 1. right, for the same instance of TPCH. And I mean, you can say, yes, maybe it's not column-oriented, or maybe it reads all the columns. It had 576 disks, right? So it's hard to argue that my my system was keeping up with this. By the way, these are times on the disk array. Now, I got a couple of days back a running time for a single instance of query 1 of 64 seconds. Multiple instances start to put a little bit more noise on the memory bus. And interestingly, you slow down even the linear scan, because the DMA controllers fight with whoever needs data, and then you slow down a little bit the hard drives. And that's literally what's happening. Okay. All right. I should so bulk loading, I'm not going to go into details. I noticed 2 days back that we can do about 2.3 terabytes per second in bulk loading. And of course, we do code generation for the bulk loader as well. Right. So right. So I have to wrap it up. Okay. So I hope I convince you that we get close to those 100 cycles per second. We have good performance for these very floating point intensive queries. And also, I hope I convince you that you need a complete end-to-end design for something like this. You need a very good I/O system, very good query processor, and you have to process multiple queries in parallel, right? Just briefly, this is what happens if you don't. If you split the plan at 2 queries, you're already slower than 1 query, and you keep on going up. You starve the system from memory bandwidth. Okay, so let me just briefly check what this guy is doing to see if it's done or not, and I'm ready to take some questions. All right, so it's done. Let's see. Right, so 602 seconds to finish query 1 on 10 terabytes, which is better than all the numbers except the 2 IBM systems that eventually get bogged down. Okay, let me put the slides up. And yes, thank you, and I'm ready for your questions.
This has the gut feel of a remake of a very old movie. I recall that the Army Art Department has their files on 13 mag tapes. Every day they would run all the mag tapes, run all the queries, run all the updates, and be ready for the next day. And this, you're pretty much reinventing it with, of course, different centuries technology.
This is like
Is it fair?
It's definitely fair. So people ask me a lot about DataPath. So I think what's new about DataPath is coming up with good basic principles and sticking to them and implementing it on modern hardware. It's very hard to say, this is new, this is new, this is new. Pretty much everything has been done one way or another, not necessarily in this combination. Okay, so that's all I have to say. And some of them are minor innovations or tricks that people might not have noticed. But this is about doing it, not so much about, like theory, make sure it's very novel. Yes?
So about that part of modern hardware, in some sense, the old hardware also was quite similar. It did not like interruptions, it did not like jumps, it did not like synchronization. However, at least databases, as we knew them, had concurrency control, where you had to synchronize somehow. You had to compute histograms, which meant you had to pick in the data, and that was also expensive. So, in some sense, why do you believe that it's now time to actually throw away, let's say, concurrency control, or not do, for example, histograms just to get that extra performance?
So first of all, I don't think construction of the histograms is necessarily in the way. So let me put it like this. I thought about this because I'm an approximation guy. There is so much CPU going around that I can actually do my own little queries that compute statistics, and you won't even notice any improvement in the overall running time, right? So I can do computing some of those caches and some of the stuff parallel to your queries because there is spare capacity, right? And getting done in kind of in between the rest of the things. So I don't think that's a problem. But so with respect to why now are we doing this, I think this paper is at least 10 years late. This should have been done at least 10 years ago because there is nothing in the hardware I'm using, except very fast hard drives. There's nothing in the hardware I'm using that wasn't there 10 years ago. Actually, it's worse. It's probably 15 because as an undergrad, I've been taught in the architecture class everything I applied to do the system. Right? So, but the difference is probably the availability of cheap throughput. You really need hard drives that pump data at rates that can put the CPU in trouble. This wasn't the case even something like 5 years ago. In the last few years, because of the SSDs, things changed fundamentally. Okay, and that's basically a game changer. Now with $8,000, I can get 2 gigabytes per second. That was unheard of before. Okay.
One more question.
So you mentioned shared scan or circular scan, and if you build a well-constructed shared scan system on like 50 disks, will perform compared to this system?
Right, so that's the point I was trying to make. If I only share the scan, but not share the data throughout the system, the data comes from the disk so fast that I can afford to read it twice. So this is the query here. So this is what I've done in the system. Instead of running all the query 6s in parallel, so consolidating the computation in a waypoint, I split the plan. So I put 2 different waypoints, query 6, and up to how many queries you want to run. So by the time you reach 2 queries, you already are a little bit slower than 1 query. Look at this line that shares perfectly everything. Right? At 10 queries, you're off by almost a factor of 7. Right? So what that means is by splitting the plan, sharing the scan, but doing independent computation, you have to read the data independently 10 times in that situation. And that basically bogs down the system completely because the I/O occupies about 1/3 of the cross-memory bandwidth in this system. So you can read it twice. You can look at it twice. Okay.
Thank you, distinguished speaker.
All right, thank you.